So good day everyone. In this video, we are going to discuss about direct proof of a conditional statement P implies Q. So how do we prove this conditional statement or implication P implies Q with this proof? So the first step is to assume that P is true or the antecedent hypothesis or premise P is true. Okay, and using combination of theorems or definition or rules of inference, we show that Q must also be true. So direct proof are quite straightforward with a fairly obvious sequence of steps leading from the hypothesis to the conclusion. So um, let us have an example. So let us try to prove this theorem. If n is odd, then n squared is odd. So the first thing that we have to do is define what an odd and an even integer is. So we say that an integer n is even if there exists an integer k such that n is equal to 2 times k. In other words, that n is a result of factoring out 2 times some number k. So for instance, if you have an even number 6, then it can be factored out with 2 times 3. If you have an even number 10, then it can be factored out with 2 times 5. Okay? So in here, in that case, the n will be 5 and the n will be 10 and the k will be 5, which is its factor. Okay? And what about an odd number? We say that n is odd if there exists an integer k such that n is equal to 2k plus 1. So we simply add 1 to the 2k. So for example, if we have an odd integer 5, then we can that may be equivalent to 2k plus 1, where k will be equal to 2. Okay, so 2 times 2 plus 1 will result to 5. If we have an odd integer 7, then that will be equivalent to 2 times 3 plus 1, where k will be equal to 3. All right, so note that every integer is either even or odd, but not both. Okay, so in order to prove this theorem, if n is odd, then its square n squared is also odd. So we can restate it as for all even numbers, for all integer n, if n is odd, then n squared is also odd. So we can rewrite it in its predicate na form. For all n, P of n implies Q of n, where P of n states that n is an odd integer and Q of n states that n squared is odd. So we will show that by showing a specific instance P of n implies Q of n. So here goes the proof. We will start with some terminologies of odd number. So we say that n is odd if there exists an integer k such that n is equal to 2k plus 1. So the proof is we start with the assumption that P is true first. So in this case, the P or the hypothesis is n is odd. So we will assume that indeed n is odd and that we will use that assumption to prove Q, which is n squared is odd. So if n is odd, then n is equal to 2k plus 1 for an integer in a k. So we will be using this P to prove Q. So squaring the both sides of the equation, we get n squared is equal to 2k plus 1 quantity squared. Okay, so we simply square the 2k plus 1. And then using a simple algebra, we arrive to 4k squared plus 4k plus 1. And now we can factor out 2 from the first terms. It will be equivalent to 2 times 2k squared plus 2k plus 1. And it has this form 2r plus 1, where r may be 2k squared plus 2k. So since 2r plus 1 has the form n is equal to 2k plus 1, which defines an odd integer, then we can say that the square of an odd number is also odd. So we have proven it using a direct proof. So let us have another example. Let us try to prove this theorem. The sum of two even numbers is even. So we can rewrite this statement into this if-then structure. If integer x and y are even, so we have introduced two variables x and y to represent the two even numbers. So if these two integers x and y are even, then the sum x plus y is also even. So now it has this conditional na form. So we will be using the definition of an even number, that n is even if there exists an integer k such that n is equal to 2k. So using the direct proof, so we will start with the assumption that p, integer x and y are even. So we set variables x and y as x is equal to 2m and y is equal to 2n, right? And now, using this assumption, we will prove that the conclusion q is true. So that x plus y, or the sum of two even numbers x plus y, is also even. So we take the form x plus y, this will be equivalent to 2m plus 2n, and factoring out the 2, we will be left with 2 times m plus n. And it has this form 2k, where k is equal to m plus n. So as you can see, the sum has a the sum may be factored out with 2 with some number k equals m plus n. So we can say that the sum is an even number. So we have proven that this theorem is true. Now, we have the third example. Let us prove that the product of two odd numbers is also odd. So we can rewrite this theorem as if integer x and y are odd, then the product xy is also odd. They should be odd. They should not be even. Okay, so let me just quickly change it. Is also odd. So we have this form. If n is odd, then there exists an integer k such that n is equal to 2k plus 1. So the proof starts with this assumption, p, that it is true. So our p, or hypothesis p, is that x and y are odd. So we then set x and y as 2m plus 1 and 2n plus 1. So assuming that this p is true, let us try to prove the conclusion that the product of two odd numbers are odd. So we have x times y will be equivalent to 2m plus 1 times 2n plus 1. So using a symbol na algebra, we arrive to 4mn plus 2m plus 2n plus 1. And we can factor out 2 from the first three terms. So we will be left with 2 times 2mn plus m plus n plus 1. And we can rewrite it with this form 2k plus 1, where k is equal to 2 plus m, 2 times mn plus m plus n. So since it has the form of an odd number, then we can say, or we have proven, that the product of two numbers, of two odd numbers, is indeed odd. Okay, so the direct proof leads from the hypothesis of a theorem to the conclusion. So we assume first that p is true and use this assumption to prove q. Okay, so however, there are also proof of theorems that do not start with the hypothesis P and end with the conclusion. And these are called the indirect proof, and we will discuss that in the next video.